a brush against the water, then agony. In northern Australia, invisible strands dangle just offshore, armed with micro-harpoons that fire in millionths of a second, pounding lethal venom straight into the bloodstream. Each year, swimmers' hearts surge and, sometimes, stop, proof that box jellyfish possess the ocean's most ruthlessly engineered kill chain. But how did a creature without a brain outsmart evolution at this scale? And could you recognize its hunting ground before it strikes? In the warm, shallow waters stretching from northern Australia to Southeast Asia, a silent threat glides just beneath the surface. These are the box jellyfish, cubozoans, and masters of the Indo-Pacific shallows. Three groups dominate these waters: the infamous Chironex fleckeri, sometimes called the Australian box jelly, mid-sized Chiropsalmus species, and the tiny but deadly Irukandji jellies such as Carokia barnesi. Each has carved out its own hunting ground along coastlines, estuaries, and river mouths where fish and crustaceans are plentiful and where people wade and swim. Chironex fleckeri stands out as the largest and most feared, with a bell that can reach up to 30 centimeters across and tentacles trailing 3 meters behind. Up to 60 of these tentacles arm a single animal, each packed with billions of stinging cells. Chiropsalmus species, slightly smaller but still formidable, haunt similar waters from Australia up through Papua New Guinea and into Southeast Asia. Then there is the Irukandji group. These jellyfish are nearly invisible, their bells barely the size of a fingernail, but their venom can trigger a chain reaction in the human body that is every bit as dangerous. From October through May, stinger season transforms northern Australian beaches. Local warnings go up, and lifeguards scan for drifting cubes. The risk is not limited to remote or wild places. These jellyfish thrive in the same calm, sandy shallows where families gather and children play. Water temperatures between 20 to 32 degrees Celsius, gentle currents, and murky conditions all create favorable conditions for their approach. Bays, inlets, and river mouths are especially attractive, offering both food and shelter. These animals are not passive drifters. They navigate with purpose, responding to light, current, and prey. In these coastal zones, the box jellyfish have become apex predators, perfectly adapted to strike in waters that look to the untrained eye completely safe. 4 compact bulbs called rhopalia sit tucked along the rim of every box jellyfish bell. Each rhopalium holds a sensory arsenal, 6 eyes apiece, adding up to 24. 2 of these eyes have lenses and retinas, much like a camera, able to form true images and track moving shapes. The others are tuned for simple light and dark, gauging brightness and direction. This is not the blank stare of a drifting jelly. Box jellies can see. They can tell up from down, follow the sun's path, and even spot the shadow of a passing fish or a swimmer's silhouette above. Hunting skill. In laboratory tanks, researchers have watched box jellies steer around pillars and avoid tank walls. They do not just bump and recoil, they anticipate, turning smoothly before making contact. Some species, like Chironex fleckeri, will even pause near the edge of a shadow, waiting for a fish to stray close before launching forward. Their vision is sharp enough to pick out mangrove roots, beach sand, and other obstacles that would snag their delicate tentacles. It is a level of environmental awareness rare among jellyfish, and it gives them an edge as predators in cluttered, shallow water. The rhopalia also contain balance organs, letting box jellies orient themselves in rolling surf or a swirling current. With this sensory toolkit, they can hunt in broad daylight or the gloom of dusk, adjusting their position and speed to match the movement of prey. Far from passive drifters, they use their eyes to map the world and plot a course through it. The result is a hunter that glides with purpose, using vision and movement to set up the perfect ambush, invisible until the moment it strikes. Box jellyfish don't wait for luck. They engineer their own success. Each animal pulses its bell with precision, driving itself forward in short, deliberate jets. This is not aimless drifting. The bell contracts, water rushes out, and the jelly surges ahead, steering through the water column with surprising control. At the same time, its tentacles trail behind, unfurling into a near-invisible curtain that can reach several meters across. Dozens of these filaments hang in parallel, forming a living net that is almost impossible to spot in cloudy or dim water. Currents and tides play a silent role in the setup. Box jellies position themselves where water movement funnels prey, small fish and shrimp, straight into their waiting trap. Bays, estuaries, and river mouths are perfect staging grounds. Here, changes in turbidity and shifting light make the tentacles even harder to detect, both for prey and for people waiting nearby. Field studies show box jellies often hover just above the sea floor or drift at the edge of sandy drop-offs, letting the flow do the work of bringing food to them. The geometry of the ambush is ruthless in its efficiency. Each tentacle bristles with batteries of stinging cells spaced to maximize coverage. When a fish or a swimmer's leg brushes against the net, contact is almost guaranteed. With so many filaments arrayed in 3 dimensions, escape routes vanish. The tentacle net does not just snare, it delivers the jelly's weaponry at the exact moment of contact. In these shallow, murky waters, the odds are stacked in the jellyfish's favor. The next step, firing the microscopic harpoons, happens in a blink, and the consequences unfold with terrifying speed. A single brush against a box jellyfish tentacle sets off one of nature's fastest mechanical reactions. Each tentacle is armored with billions of tiny capsules, nematocysts, waiting for the right trigger. When a target makes contact, these capsules sense a combination of pressure, chemical cues from skin or fish scales, and even slight changes in salt concentration. In less than a millionth of a second, the capsule's internal pressure climbs to over 10 million pascals, higher than a car tire by several orders of magnitude, and fires a coiled tubule outward. The tip accelerates to nearly 18 meters per second, faster than the blink of an eye, piercing through skin, fish scales, or even the tough outer layers of crustaceans. For years, the actual speed and force of this strike remained a mystery. Standard cameras couldn't keep up. Only recently, using high-speed videography at hundreds of thousands of frames per second, researchers captured the harpoon's journey in real time. The footage revealed a biological weapon that rivals the fastest movements in the animal kingdom. The harpoon uncoils, inverts, and drives deep, all in under a microsecond. Electron microscopy shows the aftermath. A hollow thread embedded in tissue, barbs anchoring it in place, and venom already flowing through the channel. The entire process is powered by a sudden rush of water and ions, driven by tightly packed polyglutamate molecules inside the capsule. This osmotic engine generates the force needed to break through barriers far tougher than human skin. Each tentacle organizes its nematocysts in dense batteries, especially at the tips, maximizing the chance that contact will trigger a full barrage. For the victim, there is no warning, just the instant delivery of venom deep beneath the surface before the brain can even register pain. This is the opening strike in the box jellyfish's kill chain, a mechanical marvel perfected by millions of years of evolution that turns a simple touch into a lethal injection. Venom from a box jellyfish does not just burn the skin, it penetrates deep, unleashing a molecular assault designed to end life within minutes. At the heart of this attack are CFTX proteins, a family of toxins that act like microscopic demolition crews. Once injected, these proteins seek out the membranes of red blood cells and heart muscle, punching holes straight through. The process is brutally efficient. Pores form in the cell walls, and potassium, normally kept at strict levels inside cells, floods into the bloodstream. In a matter of moments, what should be a tightly controlled electrical system becomes chaos. For the victim, the first sign might be a racing pulse or a wave of nausea, but inside, the real danger is building: hyperkalemia. With every second, potassium levels spike, disrupting the electrical signals that keep the heart beating in rhythm. The heart's chambers begin to quiver instead of contract, a state known as ventricular fibrillation. Without immediate intervention, circulation collapses. In severe stings, collapse and cardiac arrest can follow in as little as 2 to 5 minutes. Hemolysis studies show just how quickly this venom acts. Red blood cells exposed to CFTX toxins rupture almost instantly, dumping their contents into plasma. In animal models, a dose of venom equivalent to a few centimeters of tentacle contact is enough to trigger fatal arrhythmias. The timeline from sting to organ failure is so short that antivenom or emergency care often arrives too late. The speed of action can make treatment ineffective unless response is immediate. Toxicologists describe box jellyfish venom as a perfect storm, a protein engineered by evolution to bypass defenses, overwhelm the body's controls, and shut down the heart before there is time to fight back. This is not a slow-acting poison. It is a molecular weapon built for speed, precision, and total shutdown, a kill switch that can silence even a healthy heart in minutes. Agony begins at the very first contact. The sting feels like a line of fire, as if a branding iron is pressed into the skin. Victims describe the pain as immediate, deep, and utterly overwhelming. Raised, ladder-shaped welts appear almost instantly, marking where the tentacle touched. Underneath, the venom works with brutal precision. Neuroactive compounds trigger nerve endings, sending pain signals surging through the body. But this is only the start. Stress takes over within seconds. Adrenaline and noradrenaline flood the bloodstream, driving the heart rate sky high and spiking blood pressure. This catecholamine surge, meant to help in moments of danger, now fuels the venom's effects. Victims may clutch at the sting site, gasp for air, or collapse as their cardiovascular system spirals out of control. In severe cases, especially when large areas are stung, confusion, vomiting, and muscle spasms follow. The skin itself may begin to die, dermanecrosis, leaving deep wounds that can take months to heal, if at all. Milliseconds matter for fish. A brush against a tentacle, and paralysis arrives almost instantly. The prey never escapes, never damages the fragile tentacles, but for humans, the timeline stretches into a nightmare. The pain radiates, then spreads, as venom seeps into deeper tissues. The heart's rhythm stutters. Some collapse within minutes, others endure waves of agony, their blood pressure swinging wildly as the body tries to compensate and fails. Race against time is the reality for lifeguards and paramedics who respond to severe stings. They watch for signs of collapse, begin CPR if needed, and try to limit further envenomation. Survivors often recall not just the pain, but the terror, the sense that their body is shutting down from the inside. This is the full consequence of a box jellyfish sting. Not just a surface wound, but a body-wide storm, unleashed by molecules evolved to stop a heart before help can arrive. Irukandji jellyfish, like Carukia barnesi, upend the usual script of jellyfish stings. Their bells measure just 1 or 2 centimeters across, and their tentacles are nearly invisible, yet their venom can trigger a delayed crisis that baffles even seasoned lifeguards. Victims often feel only a mild prick at first, sometimes missing the sting entirely. But within 20 to 60 minutes, the body erupts into chaos. Severe, deep muscle pain, excruciating lower back cramps, pounding headaches, nausea, vomiting, and a sense of impending doom. Blood pressure can spike to dangerous heights, the heart races, and in the worst cases, fluid floods the lungs or the heart falters. Doctors call this constellation of symptoms Irukandji syndrome, a name that's become infamous along tropical coasts. Unlike the rapid collapse seen with Chironex fleckeri, Irukandji venom works more slowly but is no less devastating. The delay gives a false sense of security, turning swimmers into patients long after they've left the water. Clinical records from Northern Australia and Southeast Asia document cases of healthy adults doubled over with pain, requiring morphine just to endure the hours that follow. In rare cases, the syndrome spirals into pulmonary edema or life-threatening hypertension, even in people with no previous heart problems. Why would a jellyfish so small wield such a complex, overpowered toxin? Evolution has forced these tiny hunters into an arms race. In the fast, crowded shallows, prey can vanish in a heartbeat, and a torn tentacle means lost energy and risk of infection. The venom must work on contact, immobilizing fish before they can struggle free and damage the delicate stingers. In this world, it isn't enough to be lethal. Efficiency is everything. The same venom that subdues a fish in seconds can, by accident, send a human into medical crisis. The brutality is not a mistake, but a product of relentless selection, where only the fastest, most effective killers survive.